Good evening, ladies and gentlemen, and welcome to the SAIEE Energy Storage Chapter webinar on the operational benefits of the Steenbras Pumped Storage Facility. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. And by default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Energy Storage Chapter playlist. You will also find the registration link in the chat box. Please click on that and register. It's free. A certificate of attendance will be issued a few weeks after this webinar once we've received the CPD validation number from EXA. I'd like to also bring to your attention, you'll find in the handout section, you will find the 2023 SAIEE Training Academy brochure for your information, a PDF to be downloaded. The 2024 What Now features and deadlines. The magazine is being revamped during the holiday break, and we'll have issues running from February to November, 10 issues instead of the standard 11. And then, of course, you'll also find the What Now November 2023 in the handout section. Another thing in the chat box, you will also find links how to become a member of the SAIEE. You can click on that link. You'll find the CPD calendar, as well as the actual online link to the What Now November issue. And of course, there is the registration link to the SAIEE TV. Without further ado, I'd like to introduce you now to our host today, Ms. Naniki Nzuza, who's a Senior Grid Manager for Molilo Renewable Energy. She holds an electrical engineering degree and a postgraduate project management diploma from the University of Cape Town. As I mentioned, Naniki is a Senior Grid Manager with Molilo Renewable Project Developments, providing technical leadership and oversight on grid integration for a portfolio of projects. She is an accomplished professional engineer and a subject matter expert in the energy industry with almost 20 years of experience in power system planning and operations. Naniki is passionate about paving the way for the next generation of leaders. She's mentoring young girls to encourage them into the STEM career stream through the Girl Eng movement and the Girls for Girls mentorship programs. Over to you, Naniki.
Thank you, Minx. Good evening, everyone. Thank you so much for making the time to join us this evening at a time where most people are ramping down. But I think as we have seen in the recent weeks and months, there has been a buzz in the energy arena, starting with, I guess, the much fanfare in terms of the launch of the HEX battery energy storage, as well as what has been released last week as the award of the prepared bidders in terms of battery energy storage. I think it's on the back of that we, as the energy storage, SAIEE energy storage chapter, wanted to make an offering in terms of upskilling as well as continuous development. And perhaps for this evening, we'll be taking a walk down memory lane in terms of esteemed speaker Dion Jones, who's going to be talking to us about Steenbras pumped storage that is the first pump storage to be installed in the African continent. And to hear a little bit more about how City of Cape Town has made improvements and has made charted forward in terms of operational benefits for Steenbras and how that has assisted them in alleviating some of the stages of load shedding. Dion has a national diploma as well as a BTech in electrical engineering from CPUT, and which was a focus on high voltage engineering, electrical distribution, and protection systems. He has also attended University of Stellenbosch to qualify with a certificate in coaching. He's been working at Steenbras Power Station as an electrical maintenance manager within the Energy Directorate within the generation group since 2013. And his role is to ensure that the city's generation plans are maintained and serviced to ensure optimal usage and availability. our paths are crossing again. I know Dion from way back in our time when he was a protection specialist in Eskom, and I was a network operations analyst as well. So yeah, our paths have crossed again. I would like you to enjoy the session this evening. Take notes. Hopefully, if you have some questions, will you please put those in the question section so that we can attend to those at the end of the webinar, as well as just to highlight that the seminar is going to be offering a CPD points. So please hang with us for the rest of the seminar. And we've got there on the chat box how you can become a member of SAIEE to ensure that you still develop yourself as an engineer, and also get some back recordings of webinars that have been done as well are available on the YouTube channel of SAIEE. So these are all available on the chat box as well. Dion, I would like to hand over to you. We are in your capable hands as you open the turbine rooms for us this evening.
Hi, good evening, Naniki. Good evening, everybody. Thank you. As Naniki said, we've known each other for some time from our Eskom days, and just thank you for the opportunity to be presenting. So just advise me, Naniki, can you see my presentation? I'm going to stick it on now. Can you see it?
Just swap your display settings, Dion.
Sorry, display settings.
There we go.
That's right.
Proceed. Thank you.
Okay, so I can proceed, Minx. Is that in order?
Yes, perfect. Please proceed.
Okay, thank you, Minx. Good evening, everybody. My name is Dion Jones. I'm based at the Steenbras power station. I've been here since 2013. We form part of the energy group within the electricity directorate within the city of Cape Town. My designation is as electrical maintenance manager, and that's basically my role that I've been fulfilling over the last 10 years. So without any further ado, I'll get into the presentation. I hope you enjoy it, and please feel free to ask as many questions as possible, and I believe that we will have some time at the end of the presentation. Okay. Okay, so the Steenbras power station was initially planned for Table Mountain in the early 70s, and because of Table Mountain being a national monument at the time, that idea was not followed through on. Steenbras power station, some of you may be aware of a local endemic fish called the Steenbras, which is found in the area in Cape Town. So the power station was actually named after the fish, which was named after the river, and that's how Steenbras power station got its name. It was commissioned in 1979, and at the time, it had a rated capacity of 180 megawatt. At that stage, as well as Naniki has mentioned, the Steenbras power station was the first of its kind in Africa, and it was also obviously the first hydroelectric pump storage scheme on the continent of Africa. You get a few different types of pump storage or hydroelectric schemes. We are referred to as a pump storage. The reasons I'll go into a bit later. You also have the normal run of river, whereby you will have water that is flowing in the river. It goes then through the turbines in a power station and then exits on the other side, hence the name run of river. And then one which is called an impoundment. So basically where you have a big catchment area and typically a dam, and you control the water, and then you allow it to run through your power station also in a controlled manner. So those are the different types of hydroelectric power stations that you get, and we are referred to as specifically as a pump storage, which I will get into a bit later. Okay, so that's just an overview of what it looks like of the layout. On the left-hand side is what we refer to as the lowest Steenbras dam, and just towards the right-hand side of the smaller dam on the bottom, you should be able to see our power station situated there. And then in the middle of the photo, you will see the range of mountains there. On the right-hand side is what we at the power station refer to as Steenbras Upper. And the lower dam is 10 times smaller than the upper dam. And on the right-hand side, you might just be able to see it. There is a man-made wall that was created to enable us to control and dam up water. And then just a little bit further back on top on the right-hand side is our upper control works and inlet tower. But I will get to that a bit later. So we are located in Cape Town, halfway between the N2 and Gordons Bay Beach. And we're situated on what is referred to as Salaris Pass Road. Okay, so that's just a side section or a view of a cross-sectional profile of what the setup looks like for our power station. So let me start on top. Okay, so on the left-hand side, as I showed you on the previous slide, is our upper control works. And also at the start there is our intake works in the dam on top there. So we are connected via a series of tunnels through the mountain. We engineered through the mountain and then all the way to the bottom part, which is the smaller dam on the bottom in the yellow portion. You may be able to see our power station located at 8 and 9 over there. The portion labeled, the section labeled between going through the mountain, going horizontally through the mountain, is referred to as your low pressure tunnel. And then as it gets closer to the power station, it becomes narrower and is reinforced with steel. So we at the power station, we sit approximately 60 to 70 meters above sea level. And then it's a further 300 odd meters to the upper control works with the bigger upper dam on top. So the water in the upper dam or upper reservoir labeled as 1, I'm not sure if you can see it, but on the left-hand side of the photo that is up at the moment, it is obviously utilized for our storage scheme. But a portion of the water then also goes via the man-made dam wall over there, and it goes further onto water treatment plant. And those of you that are familiar with Cape Town, if you are in Gordons Bay and you look up onto the mountain, on Clarence Drive on Route 44, you will be able to see the upper control works there. So where sort of halfway, you will have a vertical piece that joins the horizontal piece, and that is referred to as your surge shaft. And that just ensures that if there are any buildups of pressure within the system for whatever reason, that there is a pressure relief point or pressure relief valve basically to ensure that there's no damage to plant and no damage to the tunnel as well. So at the upper control works, it is obviously water that comes from nature. We have a screening chamber up there, which allows us to filter out branches, leaves, and even sand, and not sand, but small rocks and those kinds of things. At the upper control works, I've got a photo which I will show a bit later. We have two gates up there. We have a duty or a main gate and emergency gate. And these gates can be operated automatically by the control systems that we have at the power station. Or alternatively, in the event that we need to operate it manually for whatever reason, in the event of an emergency, or perhaps we're doing some gate maintenance, or often we once every 5 to 10 years we have some tunnel outages, then we are able to also operate it manually as required. Okay, just for those of you who are interested, there we have some specifications of the upper waterworks or the upper control works. As I said, it is 10 times bigger than the lower dam on the bottom here. The upper reservoir capacity is 30 million cubic meters. The gate is approximately 3 by 4.5 meters, and the rate of intake is about 5.4 meters per second. The tunnel length from top to bottom is about 813 meters. And then the third shaft, which is sort of sitting in the middle, which I referred to, the shaft diameter is 10 meters and at a depth of 36 meters. And then the tank of the surge shaft is 20 meters at a depth of 8.5. The vertical shaft, which joins the high pressure tunnel to the low pressure tunnel, is approximately 120 meters long. Okay, so just a couple of photos in terms of our setup at the power station. The top photo is us, that is the power station where we are situated, and I'm in fact currently sitting there at the moment doing the presentation. This is the lower dam, the water that you see here, and the two buildings on the bottom here are referred to as our lower gates, outlets, and that is where once the water exits the power station, it comes through the 4 separate gates and then enters into the lower dam. On the bottom left-hand side is just a part of our rotor and a part of our runner. So that's one of the biggest mechanical components that we have at the power station, and that is the part that the water is funneled through and causes the rotor to rotate, obviously, and that's how we are able to generate. In the middle, the green equipment there is the lowest part of our power station, which is found in the CW or cooling water basement. So obviously with an engineering piece of plant as big as ours, we have a lot of moving parts, a lot of mechanical parts that need to be kept fairly cool. So what we do is we have our own CW intake, and we take water from the lower dam, as shown in the first picture that I discussed. We then send it through a system of filters and strainers, and then we are able to send it onto the water bus throughout the power station, and it's utilized for various activities throughout the entire power station. The photo on the bottom right-hand side, I just put it down as an example of the types of switchgear that we have here. So this is just an example of the 380 volt fused switchgear that we have. And on the bottom right-hand side is just another example of some of the electrical components we have here. I will go into detail a bit later. Excuse me. So on to the next slide. So we run at, we have 4 machines. We run at 600 RPM, and each unit is rated at 45 megawatt. As I mentioned a bit earlier, that we are there's approximately 300 meters between us at the power station and the elevated dam on top of the mountain, which I showed you in a previous slide. The original machines, the generators were developed by a company called Siemens from Germany at the time, and the pump turbines was developed by an Austrian company called Escher Weiss, and they are still the original make even today. Then in terms of stored energy, so what that refers to is if you consider the lower dam as a sort of a battery storage in terms of capability to be able to store water that has been used, we are able to store just over 2,200 megawatt hours in the lower dam on the bottom. As I discussed a bit earlier, the size of the lower dam is close to 3 million cubic meters. And then, as I said earlier, the upper dam is 10 times bigger, which would then make it 30 million cubic meters. And there's a conversion to liters from that. So that's some of the plant data just in terms of the high-level setup. Let me get into a bit more detail. Okay, so as I said, we consist of 2 reservoirs. We have a lower dam at the power station and then an upper dam on top. Water is reused and it doesn't enter the sea or enter back into a river. So the water that you saw on top of the mountain, it comes through the tunnel system, or what we refer to as the penstock. It then goes through all of our generators, and it is then released via the draft tube into the lower dam. In generate mode, we use stored water in the upper dam to generate electricity during peak periods, and in fact, we are currently doing that at the moment. I think we are running 2 machines at the moment, so we utilize the effect of gravity down the penstock and into the machines to be able to allow us to rotate the rotors, the massive 50, 60 ton rotors on our machines. So we will run till about 10 o'clock tonight, and then we will switch off. So our power station doesn't allow us to do 2 modes at once. We can only do either generate or pump. So we're not a dual mode hydro pump station. So coming tonight at about 10 o'clock, we will then switch off from gen mode. We will change around to pump mode, and we will then be taking power off the grid, which will then enable us to be to be able to move the water that is now in the lower dam all the way back to the upper dam for use again in the morning. We used to be, or we are referred to as a peak load power station, but due to load shedding, the profile of our usage has changed quite dramatically. So we still consider ourselves as having been built as a peak lopping or peak load power station. But yeah, as we're all aware of the effects of load shedding, so we're running quite a bit, and I'll get into that a bit later. The power station has a round trip efficiency of between 70 to 80%. One of the big advantages is that from standstill in the afternoon, when we come online at about 4 o'clock, we can get up to full speed and unload anywhere from 3 to 5 minutes, 3 to 4 minutes, just depending on the skill of the operators, because there is still some manual operations that need to be done. And we can get up to 45 megawatt within 3 to 5 minutes and synchronize to the grid. With load shedding and grid instability at the moment, we do find that we have some issues in terms of synchronizing our units onto the grid, and that's where a little bit of time is spent, and it takes quite a bit of skill to be able to get it onto the grid and generating. Another advantage of the power station, it is obviously because our chief usage, as opposed to a coal power station, we are using water to be able to generate, and so there's not no pollution and waste, but there is a considerably minimal amount of pollution and waste. One of the major drawbacks that we have currently, as I said, that we have the massive water on top, and in fact goes further to Palmit, and so we have almost unlimited water on top of the mountain. But the biggest operational limit that we have is that we are limited to 2,200 megawatt hours on the bottom of the dam, because the dam has obviously got a certain physical size and profile and contour, and it can only take X amount of liters over a period of time. So we are currently within the city and within other departments, other directors, looking at options in terms of how can we change that. One of the things that we're looking at doing is perhaps changing the profile of the dam and opening it up, making it a bit bigger. And then another option is to see, can that water be drained off and used somewhere else. We do have a facility to drain off or run off some water to a 4A treatment plant in Blackheath, which is about 35-40 kilometers away from here. But we are not able to run off fast enough and enough so that it makes a massive impact on the lower dam at the bottom here. Okay, we provide security of supply because we're able to come online so quickly, and should there be any issues with supply from Eskom or any other sources, we can come online fairly quickly. At full load, if we have all 4 machines available, we can run for about 12.5 hours at 180 megawatts. And then obviously, as I said, after running for that amount of time, the lower dam then will fill up and we will have no space on the bottom. So at the moment, we are used to supplement Eskom energy supply. And I think the big thing out in the media and within the city and the province is that because of Steenbras, chiefly because of Steenbras, that City of Cape Town is able to mitigate anywhere from 1 to 2 stages of load shedding, just depending on what the national load shedding levels are at the moment in time. So the photo on the right-hand side is just those that are not familiar with Cape Town, because the power station was built in the late 70s. Obviously, the city wasn't as developed or as urbanized as what it is today. And then additionally, the distribution network and transmission networks were not what they are today. So at the time, the closest point that we could import and export was to an area called Mitchell's Plain substation, which is approximately 50 kilometers away from our power station out in Gordons Bay. That was up until a couple of years ago. So one of the chief reasons that we had to change is because Mitchell's Plain is a very urban area, very populated, and obviously a lot of developments and growth happening there. And at night, when we were required to take power off the grid to enable us to pump up again, it became a major issue in the Mitchell's Plain, Philippi, Guguletu, southern suburbs area that we refer to here in Cape Town. And so the city put in place plans to be able to have another import-export point for Steenbras Power Station. So with that, along the N2, about 15 kilometers away, which is what I've got up at the moment. A substation, a 132 kV substation, was built and developed, and that is currently where we now import and export to into the new Part de Vlei substation. My next slide just shows, I hope you can see it, and I hope it's clear enough, but Steenbras has 4 units at 45 megawatt onto our 132 kV bus bars. And then from there, as I said, we've got 2 feeders going out to the relatively new Part de Vlei. And then we now are closer to the Helderberg area. So if you look at the Part de Vlei bus bars, we're about 15 kilometers from there. Mitchell's Plain, we still have a connection to it via Part de Vlei, which is 50 kilometers away. And then on the top in blue is the Pinotage Eskom substation at 132 kV level. So we are able to go all the way to Eskom if we should need to take power from Eskom into Steenbras power station. So the redesign of the network has given us a lot more flexibility in terms of how we are able to operate, and then also alleviating a lot of the issues around overloading in the Mitchell's Plain area, specifically peak times and in the evening. So, okay, coming down to the power station, this is a cross section of the building. The building dimensions, it's about 90 meters by 40, and then from floor to roof is about 20 meters. We have 4 machine sets, which consist of 2 shafts. So it's shaft A and shaft B. And then in shaft A, we have unit 1 and 2. And then in shaft B, we have unit 3 and 4. And then obviously 4 times 45 gives us the 180 megawatts. So from floor level down to the machine level, as you can see, labeled as 1. I think you should be able to see it. That's about close to 46 meters. And then the shaft is about 20, each shaft is about 20 meters in diameter. Just to give an idea. So that's an old photo of the power station when we were busy developing it. And then on the far end, you can see that is shaft B. And then just on the bottom left-hand side, you can see shaft A. And then on the floor, many of the components which currently reside inside the power station were on the floor there. So, but I'll get into some of them a little bit later. Just to point out that on top, we have a crane rail system, which was installed at the same time that the power station was developed. And it's quite an important bit of machinery. It's an 80/15 ton crane. And it allows us to obviously be able to work into the shaft to remove and to replace all components down there. So when we do our yearly summer outages, it's quite important to have that bit of plant available. As you can see there, I think that is in fact, a portion of the rotor and the rotor poles that they are busy lifting there. So the heaviest part of our plant down there is in the middle there's the rotor pole, if I'm not mistaken. We're coming in at about 40-45 ton. And then each of those 10 poles around there weigh about 2.2 tons. So in total, you're looking at about 60 to 70 ton that you need to be able to lift. But normally we remove the rotor poles and lift them out individually on their own. And as long as I've been here, we've never lifted out the entire rotor. We only lifted out portions of it. So, okay. So also, I will touch a little bit later, but we're looking towards refurbishment in the coming years. So obviously the crane will play a critical role. And because of the age of the crane, we were running into quite a few problems, but fortunately we've been able to get a tender in place recently. And so we were hoping to execute in the next year or two, so that down the line for normal maintenance, normal breakdowns, as well as looking forward into the future, into the refurbishment, that we will have a reliable crane available. Okay, coming further down now onto the machine. So that's what the machine looks like on the display there. Just on the left-hand side, it's what I was trying to show there is what we refer to as the main inlet valve at the bottom of our power station. And that on the drawing or the diagram on the right-hand side, that is labeled as 2. So that is your main inlet valve. So we've got one penstock or one tunnel system coming down from the upper control through the mountain. Then when it gets to the power station, it splits or bifurcates into shaft A and shaft B. And then it further splits again into unit 1 and 2 and unit 3 and 4. So the term that we usually use there for the split is referred to as the bifurcation of the pensock system. So on the right hand side of the drawing labeled as 2, that's your MIV. So each individual unit will have its own main inlet valve, and simply put, that is the valve that controls the water in and out of your machine. So it's literally like a massive tap, and that switches on the water going in and out of your machine. It's a lot more complex than that, but that is basically the principle behind it. Labeled as 1. So the top portion, the bottom portion of 1 is the heart of your machine in terms of the mechanical components. You have what is referred to as your pump turbine. So because we are reversible, it either acts as a pump or as a turbine, depending on which mode we are in. And so at the bottom here would be referred to as your pump turbine. The third portion would be in the middle here, which is the heart of your electrical component. So inside section 3 here would be your gen stator, and also then your rotor rim, rotor hub, and your 10 rotor poles, which I've shown you on the previous slide, but we will show some more photos a bit later. On top of the unit, each of our machines have what we refer to as a pony motor, and the pony motor serves a dual purpose. So when we operate under gravity, we are generating, and we do not use the pony motor to start up in generate mode. We utilize gravity. At the end of the run, when we're shutting down from generate mode, the unit is obviously running at 600 RPM. We then shut down, we close down or close off the MIV at 2, and then the system runs down to under gravity on fairly important bearings, pressurized with oil. It runs down to about 340 RPM. And then what happens is that the pony motor acts as a dynamic brake, and it basically counteracts or opposes the inertia or force applied by the turning shaft. So it's just to get the machine to run down a lot quicker. We can operate without the pony motor in generate mode. It will simply take a lot longer. So instead of shutting the machine down in approximately 4 to 5 minutes, the machine will run down on its own weight, still on the bearings that are lubricated and under air pressure. And that takes anywhere from 15 to 20 minutes, depending on the different characteristics of the bearings in each individual machine. So that's the one purpose that the pony motor serves. The more important, so we can generate without the pony motor. The more important purpose of our pony motor is that at night, or when we are required to then pump and send the water back up, we cannot rely on gravity. So the pony motor then has to run the rotor up to 600 RPM. It has to then start building up pressure against the MIV, or against the pressure or net head on the MIV. It has to then be greater than the head on the other side of the MIV. And then when that happens, we can then overcome the downward force of the water due to gravity, and it will push it up, and then we start pumping up in the other direction. Okay, so that's the machine set. That's just giving you a visual view of what it looks like. So just on top here, where you see the yellow beams of the crane, on top of that will be the lower guide, and that's where if you climb into there, you will get the gen stator and all the rotor poles. And this green portion here on the bottom, around the yellow railings towards the bottom, is the portion that I showed you now. It's referred to as the pump turbine at the power station. Okay, that's just a nice photo of the cross section again. So on the left-hand side will be the lower dam, and then you can actually see a nice representation of the gates there. Those are the control systems above the gates there. The CW basement is here on the bottom that I referred to, where we take water in. And then you can see the big pipe work and the bifurcations on the pipe work, which I was referring to a bit later. On the bottom is the pump turbine and then the gen stator. If you're coming up to floor level now, you can see at the back sort of the power components. We have all the transformers at the back, and then a lot of switchgear and control room here. So I just thought I'd include this because it's a very detailed drawing, and we have it in the foyer here. So if you ever do visit, it's quite impressive to see this. I know it's a bit small here. Okay. And then just to give you an idea of the complexity of the system, this is the diagram for our hydraulic pump control, and this is basically the mechanical heart of our system, and this is the system that interfaces with your electrical and instrumentation and allows you to operate, to run your machine up and down. So it consists of a number. So we're running two modes. We are either able to run up automatically via a PLC or an auto sequencer, or we are able to do it manually from the control panels or from the control room as well. So typically, if everything is working well, everything is automated, but with age and wear and tear and all the things that we're picking up, we're finding more and more that a lot of things need to be done manually, and it takes quite a bit of skill. So essentially, the hydraulic control is just a system of checks and balances. So all the signals from the plant come back, and all things have to happen in a very specific sequence. On this diagram, you will have all sorts of valves like shuttle valves, check valves, directional control valves, NRV, PRV, emergency valves. You'll also have massive accumulators, which is used to store energy, typically in the form of compressed air, cylinders and pistons used to operate our servos, which allows us to direct the water into the machine. All sorts of gauges, which allows us to measure values on various systems. We obviously have to monitor oil, water, air, flow, all sorts of things in the power station. A lot of pressure switches, temperature gauges, hydraulic pumps, strainers, filters, level switches, etc., etc. So I just wanted to give an idea that yeah, it's very, very complex, and yeah, it really takes quite a bit of skill to understand it and time to understand it. Moving on, just high-level technical specifications in terms of the units that we have. The pump turbine that we have is of the reversible Francis type. We generate at 45,000 kilowatt or 45 megs. When we gen, the rate of water flow is about 19 cubic meters per second, and then just a bit further down, in the pump mode, we are operating at about 14.5 cubic meters per second. Okay, and then last line, maybe of importance, or just for intersect, the pony motor that we were referring to a bit earlier, the one that sits right on top, operates at 2,500 kilowatts. When we run in pump mode, I know it says 46,500 here, but it is a little bit more. We generally, when we have to pump at night, obviously it's going to require more power than what we can generate. So we always run at a net loss in terms of kilowatt and megawatt hours produced at any stage. We usually take about 52 megawatt per unit to get the water pump back to the upper reservoir again. Okay, that's just an old photo of what the MIV looks like, and the size of the MIV is quite impressive. It's about 1.3 meters, and each individual unit of the 4 units has its own MIV, so there's one per unit. And then this is the portion that is, eventually goes out to your MIV. It's referred to as the pump turbine spiral casing, and so that allows your water to be channeled into your runner and then into your guide vanes and into your machine eventually, which causes your excuse me, which causes your rotor to rotate under the force of gravity. In 2010, 2011, we upgraded our 4 gen transformers. So each generator or its own individual transformer, rated at 60 MVA, and it's at a ratio of 12 to 132. We don't have a 12 kV busbar here. We have a 132 kV busbar, 3.3, 380. But we gen off our stator at 12, and then it gets stepped up to 132. So that's just in terms of our transformers. We have 4 individual gen units at 60 MVA. We have 2 smaller, relatively smaller station transformers at 7.5 kVA, 132 to 3.3, and then for our local supplies at the power station for various things, we have 2 common services transformers at 2 kVA, and they are rated at 3.3 kV to 380 volt. Okay, so that's just a bit more information. We have SF6 at the power station, which was installed at the inception of the power station. Has been here since, it's the same vintage since 1978, and it's served us well. So yeah, we're picking up more and more problems with the switchgear, and we're trying to get sort of services in place for that, but it served us fairly well to date. And I think just of interest on the bottom, perhaps just some stats on the cooling water system, which we run here. So the maximum cooling water demand that we can meet is 250 liters per second. And it gives the pump rating there as well. And then we obviously have some drainage and dewatering in the event of having some sort of failure or emergency. So the drainage pumps can operate at 2 times 20 liters per second, and then the bigger ones, in case of a massive rupture, which will just give us time to get out of the power station as the shaft will start to flood, runs at 2 times 135 liters per second. Okay. Then I just wanted to put this here. I know you cannot see it, but I just wanted to also again give you a feel, an idea for the size and complexity of the electrical network at the power station. As I said, we gen out at 12 kV and we step up to 132, but we don't have a 12 kV bus here. We've got a dual 132 kV bus. We've got a 3.3 kV bus, and also a quite extensive 380 volt bus. So at the top of the diagram that I have there at the moment, the 2 feeders going out there, they used to go out to Mitchell's Plain, but they now go out to Paardersvlei. And then, so the 2 feeders feed onto our busbar A and our busbar B. On the left-hand side of the diagram would be a representation, an electrical representation of one of our 60 MVA gen units. And then on the bottom there, you'll see the gen unit with the sign signal over there, and then all the protection attached to that. In the middle of the drawing, we have our 2-station transformers, which is 132 to 3.3, and then towards the bottom we have our 3.3 kV bus, and that's where all the local supply gets run from. And then on the far right of that 3.3 kV bus on the bottom, we have what we refer to as our pony motor, and our pony motor runs from 3.3 kV supply. And you may or may not be able to see the variable resistance on the pony motor. So we have what we refer to as a liquid starter, which sits on our pony motor, and it varies the resistance to be able to match what the pony motor needs to do. We do also have an emergency incoming supply coming in from Furlands on the bottom, from the water pump station on the bottom. So if we, for some reason, lose our distribution network Paardersvlei, then we are able to have some bulk supply coming in there. And then in addition to that, in the very middle on the bottom of the diagram, there is another small little gen that sits there. We have a local emergency diesel generator which operates at 800 kVA, and so we are able to get our units away if we are required to do that. So just a high-level layout in terms of what our electrical network looks like at the power station. You guys still with me? Okay. That is just at installation. So that's an example of the stator on one of our motor gensets at installation, and we do maintenance on that quite often with our summer outages that we have every year after winter. That is just a photo of our Steenbras control room. So we do have a local control room at the power station. We are required to monitor, meter, and then control everything that goes on within the power station. And that is just a view of what the control desk looks like on the bottom part of the photo. And then on the back end is what is probably referred to as a mimic. It's a very old, probably what we used to refer to in protection as phase 1 type technology. And so a lot of the parts are actually still mechanical parts, and yeah, still working, still serving us well, but yeah, we need to get to refurbishment sooner rather than later. So as I said, we do have a local control room, but we are under the auspices of the bigger control room, which runs our distribution network, and they are based at our sister control room, or the bigger control room, and they will then advise us in terms of operating and when to run and when not to run and what to do. So. Okay, so just a quick rundown. That's on the far left-hand side of our control board in the control room, and that's just an indication of the hydraulic system and the dam level. So if you look on top of that photo, you will see it's important to know the upper dam level and the lower dam level so that we know what the net head is, and in terms of whether we need to pump, and there's a whole system behind it, which I will get into a bit later when we look at the operating. That there's then just the yellow line on top is the 132 kV, the two 132 kV buses. On the left, you can see the two gen units, and then the white little boards there on top are the new Power Fly 1 and Power Fly 2 feeders. And then in the middle is the 3.3 and 380 bus, and then in the middle is the small little emergency diesel gen that we have here. So that's just the electrical side of it. And then this is the CW cooling water systems that we have here. If you count from left to right, there are 4 equivalent units. So you will see that this is where we monitor all the water. And next to that meter on the left-hand side there, you will see that there are 2 arrows facing down. That is what we refer to as your duty motor. So they keep your bus pressure where it needs to be. And then the 6 CW pumps, big CW pumps that come in as and when needed when the units start running and we need to increase the pressure. So, and then on the bottom, you can see the bottom end of the machine or the draft tube where the water exits once it exits or enters out of the machine. So, okay, that's an example of what goes on our control floor. So that is where all our PLCs sit, all our indications. And then on the top right-hand side, you will see, I don't know if you can see it, but you will see all the meters on top that we measure all of our quantities here. And then on the bottom are all the push buttons that we utilize to be able to open and close various things in the plant and get the plant away. And then on the top photo again, on the left-hand side is all the temperatures within the plant. So I thought I just wanted to show that. And then on the bottom right-hand side is our alarm and indication panel, which is very important, that guides us in terms of where we go and what is going on the plant. Okay, just at a high level in terms of the power station plant, my boss is the head of generation, so he's responsible for our power station. And then I'm not sure if you are aware that we also have 2 gas turbines that we run also, one at the old Athlone power station and then also at Rochabai. And then the head of generation is then also responsible for the decommissioning of the old Athlone power station. The staff complement that we have is around about 61 people at the moment, and we divide it up into various groups. So we have the operational coordinator who is responsible for operating and running the plant, and those guys work on shift. So we have people sitting in the control room 24/7 right around, and then also people that are working on the plant. And so it is an unmanned plant, but there are certain things that requires human input, and so we always have staff on site. Then we have an admin and clerical group. We have a projects group which was formed about 7 or 8 years ago, and it's becoming more and more important because we are having to do more and more things at the power station. So more and more projects are being formed and taken through the process, and then also looking into the future in terms of what the city wants to do within the generation space, that we need to prepare ourselves and skill ourselves for those things. And then we have 2 maintenance departments, the mechanical maintenance department and then the E&I department, which I am responsible for. Oopsie. Okay, so I'm just going to get onto the operational usage and dispatch of Steenberg Power Station. I just put some of these photos here because you cannot get them on the internet, and I just thought of interest. So the first one is the upper mountain, upper control works, upper reservoir, and that is just a picture of where our inlet tower sits. And then to the right of that is that inlet tower. You see the tower on the right hand side, and the actual inlet intake works it's referred to, and that's where the water enters the penstock down its way into the penstock to the power station. On the bottom left is an example of when they were working inside the mountain, inside the tunnel, busy with construction there. And then on the last photo there on the right hand side of the hole in the ground, that is the vertical shaft, surge shaft that sits between the low pressure and the high pressure tunnel. So I just thought I'd show that for interest as well. So okay, so just in terms of how we operate, so between ourselves, the City of Cape Town and Eskom, we set the demand for the week or the month based on historical data. And in this instance, it's the red line, so that will be the peak demand that we require. The purple portion, which is the majority of this graph here, is the grid power demand, and it shows you the cycle. So if you look towards the left here, that you will see the demand for power is lower in the morning, and then again lower in the evening, and then you have your 2 peak sort of probably between 5 and 9 in the morning, and then again in the afternoon between 6 and 8 in the evening. So the purple portion will be what the city's grid requirement is. Then the turquoise color, which is just a small portion of it, that would be in the evening when we are taking power off the grid as well, which enables us to then pump back up. So as I said, we take about 51, 52 megawatts per machine. So we are taking off the grid at night at lower demand periods and then pumping back up. So the important thing in terms of the agreement between Eskom and City is that we don't exceed the red line, which is the MMD. And in this example, it was set at that time at 952 megawatts, but it varies depending on a number of circumstances. And so we have to ensure that we stay below that line. The yellow portion is when we at Steenbras are called upon to generate and dispatch our units. So again, you will see we are utilized in the morning and in the evening in the first and the last peaks, and then on top of the yellow, you'll see a bit of red, and that would be when we dispatch our 2 gas turbines at Athlone and Rockbar as well, in terms of having to satisfy the demand for load over there. Okay. Just given an example. So on the left is Athlone gas turbine, and on the right is Rockbar gas turbine, which is situated just opposite the CTICC. For those that are not aware, so Athlone is the older machine, older Olympus machine, and it runs about 35 to 36 megawatts. And then on the right hand side, Rockbar is a bit newer and in better shape, so we sometimes get 38, 39 megawatts as and when required. We power them off jet A1 fuel, and they are very expensive to run. They consume a lot of fuel. I think they run at about 15 to 16,000 liters per hour. So it's very, very seldom that we operate these units, but as and when needed, they are available if they are healthy. Okay, so then just going to how we dispatch our Steenbras units and why we are of benefit to the city. In terms of how we operate operationally. So, so this is what is referred to as the Eskom tariff time of use. So on the left-hand side would be your low demand season or your off-peak. And then on the right-hand side would be your high demand or your on-peak. So on the left-hand side would be, at the moment, we're in low demand. So typically on a weekday, we would, let me start in the morning. So the red portion, we are required to gen from 7 to 10 in the morning on the left-hand side. And then the yellow is when we go into standard again, and then we run from, we don't have any units typically running from 10 to 6, and then the red portion again in low demand from 6 to 8 we run again theoretically, and then we swap around at 2200 hours at 10 o'clock at night and start pumping again. So this is theoretically how it's supposed to be in low demand season. Similar principle on the right hand side when we go into winter or high demand days. So it just shifts a bit early because of the time. So from 6 to 9 in winter, when we will run through peak, and then from 5 to, what is that, 7 in the evening. So this is what it's supposed to be in theory, but yeah, it's very different in reality. That often we have units that are having to, multiple units that are having to run through summer, through winter, through low, through high demand, non-stop, which creates a lot of issues in terms of plant status and managing the assets. Okay, so what this is trying to show is, as I said, we've got a number of modes, but the 2 main modes is we run from standstill to gen. We're able to get up to full capacity in about 5 minutes, and then when we shut down from gen, it takes about 5 minutes. Pump is a bit longer because you have to build up the pressure against the tunnel, so it takes around about 10 to 15 minutes to be able to pump, and then also a bit longer to shut down. So if we start on the left-hand side at 0030, that is when we typically have 3 or 4 units running in winter or in high peak demand, which corresponds, we will run from 12:30 at night to early hours of the morning till about 5, 6 o'clock in pump mode. So we're busy pumping from the lower dam to the upper dam. Then in the morning, we will shut down at about 5, 6, after 6, and swing the units over for the morning peak to gen. And then round about 10 o'clock, we will come down to fewer units. So this is what it looks like. Sorry. This is what the strategy is for running our units in winter. And we unfortunately sometimes in winter are having to run 2 units, sometimes 3 units through the day peak from 9:30 all the way to 4 o'clock, and then we bring the balance of the units online as well. Some days we run all the units all day, and all the way from 6 o'clock in the morning to 10 o'clock at night. And then there's this red circle I just used to show the swap around between gen and pump. So there's a bit of a delay, obviously the 10 to 15 minute delay to swap modes there. Okay, so that's what it looks like in high peak or in winter periods. The next graph just tries to show you what happens with the dam level. So typically on a Sunday, we will have the lower dam as empty as possible so that we have as much capacity or ability to store as much water as possible on the bottom. So you will see that we start high at the capacity in terms of what we are able to do at 2,200 megawatt hours. Then we run on a Monday, run on a Tuesday, etc., etc. So we don't pump back all the water that we gen. It takes too much energy and too long. So for every hour that a unit is able to generate, it takes an hour and 20 minutes to pump that same volume of water back up. So hence you will see the declining peak on Tuesday, Wednesday, Thursday, all the way into the weekend. That's the blue line on this energy capacity graph. So that's what it's trying to show that. And then come the weekend, so Saturday evening, Sunday, we will then try and get it back up to the 2,200 megawatts capacity again on the lower dam here. Okay, then this is what we look like in summer. Again, normally in summer we will have a major unit outage, so we won't have all 4 units available, which is what this graph is trying to show. So we will have 3 units available, and a similar principle that we still generally pumping in the evening with the units that we have available. And then morning peak from 5, 6 to 10 in the morning, we will then gen and then shut off. But as I said, because of load shedding and various other things, that we typically run a unit or 2 units all the way through to the evening and then swap around again for pump. So similar principle. Yeah, I think that's about it for that. And then also once again, it's just showing that because we are generating less and in off-peak periods or in summer, that we are able to keep more capacity availability in the lower dam, and this is essentially what it is showing you. So that come the end of the week, that we are still able to generate. Okay, so just at a high level in terms of why, as I said earlier, that in terms of power usage, we're always going to be a net power consumer at the end of the day, because we take more power to pump up than what we are able to generate. But just looking at the tariff here, just to give you an idea of why Steenbras power stations is so important in terms of the way the city and the municipality operate. So what I'm not sure it's 100% accurate, so don't quote me on this, but what it's trying to display is that when we generate peak times, we then make money at a certain rate. So the example that I've given you is that we will maybe per kilowatt hour operate at 530 cents or 530 per kilowatt hour for the periods that we are generating. The beauty of the power station is that at 10:10 at night, we then go into off-peak, and that's when we take power off the grid, and either internally to the city, the funny money, or to Eskom, wherever we're getting that power from. We then obviously pay a lot less to be able to pump back at night. So sometimes it's 2 to 3 times less than what we are getting for generating. So the Steenbras power station, yeah, does in terms of financial models. I mean, it's out there in the public. People know about it. That it does, in that sense, then bring in a lot of money for the city, and we are then able to pump it back into the power station or cross-subsidize into other requirements within the city. Okay, so just sort of coming to the summary of in terms of how we operate. In summer, we have 2 units are reserved for load shedding. We typically have 1 unit out for maintenance, and we perform peak load shifting operation. In winter or high season, we have 1 unit reserved for load shedding, and we don't do maintenance in the June, July, August winter period. And then we have 3 units to perform peak load shifting functions through the winter period. So obviously the winter periods being our most important time of the year for many reasons, and we try to make sure that all 4 units are available for winter period. Just getting onto some of the interesting maintenance and technical items which you guys may be interested in. Obviously, the plant is getting old. It's been running for long. It's starting to wear down. We used to do maintenance once a year on a unit, and then what we used to do is on the left-hand side, what it's trying to show is that so that is your rotor hub, rotor rim, and then the small little units there on the side of the circular exterior. Those are indications of your rotor poles. So we used to take all of our rotor poles out, put them on the floor, do some extensive work on it in terms of just making sure that all the valves are correct, and then do some NDT testing on it and all of those sorts of things. And then in addition to that, we would inspect the rotor rim to make sure that everything was right. The rotor rim is where the rotor hub attaches to the rotating rotor. And then in addition to that, with the outages, the other major thing that we used to do is state inspection. So generally, the 4 machines over the almost 50 years that it's been operating, the state has remained in very good condition. And so we tend to have few problems with that. The big problems that we've developed over the years has been on the parts that are taking most of the stress and the rotating parts. So at the end of 2022, when we did our outages again, the insulation on the rotor poles gave up the ghost, and so we had to come up with another plan. And so the decision, with permission from our superiors within the city and city manager, we then decided to do a full rewind on all of the poles on one of our machines. Normally, as I said, we would just do the welding maintenance and then just do the NDT checks, but because the insulation has given up the ghost after all of these years, we then were in a position where we were forced then to do a full rewind of all the poles. Then in addition to that, over the years, what has happened, because a lot of the major parts that rotate is obviously metal. There's been metal fatigue, and so we've had to keep a close eye on that. And I think what the diagram is trying to show here is when we do NDT testing, that we were picking up certain cracks that we had to monitor quite closely with our outages. We then, in conjunction with Voith, who are the OEM on our unit, we approached them a couple of years ago and then asked them, what do we do in terms of the cracks, because we were limited to how many cycles we could run due to the cracks that was starting to show on the rotor hub. And so Voith then, let's move on to the next slide here. So Voith came up with a design for us. So what they did is they redesigned or recontoured the hammerheads on the rotor pole, and so that's what that diagram on the left hand side is showing. So we did some adjustments to the actual rotor pole, and then also the slot that it goes into, which is referred to as the rotor rim. That is what it's showing on the right hand side. There was some very precise machining that was done on the units, and so that was quite an extensive exercise which we entered to at the end of 2022. We did our first 2 units, unit 1 and 2, and then similarly we did unit 3. We're busy with unit 3 and 4 currently, and they're busy being brought back to service. So we only have 2 units available at the moment. So yeah, it was quite an interesting thing, very complex, where they did finite element analysis, FEA analysis, and ran it through all their computational programs. And then let me just show you the next slide. And so this is, so on the right hand side is the cracks that I'm referring to in the rotor hub, which became of concern on all the machines, obviously due to aging and stresses. And so with the help of Voith in Europe, they then looked at all of these things for us, and then redesigned the contour as I showed. If you look at the photo on the right hand side there, that groove that's running through the middle didn't exist before. So at a high level, what that did was that it just basically moved the stress points around within the machine. And then what the graph on the left hand side is showing, so if you have a crack of a certain depth in millimeters, then if you identify it on your machine, you are safely allowed to run for X amount of cycles. So with us machining and redoing the rotor poles, it's given us the capability or capacity now to run all 4 of our units at the end of these 2 outages for quite a few more thousand cycles, which equates to, depending on how often we have to run, which equates to anywhere from 4 to 8 units, 4 to 8 years additional on each of our units, which will hopefully get us to refurbishment, which is the next thing that I'm just going to touch on. Okay, so in the early 2010s, the city took the decision that Steenbras needed to be refurbished, and just in terms of the objective there, or the mission plan was from the city of Cape Town to evaluate the status of the installed plant at Steenbras and report on the most economically viable plant refurbishment and optimization scenario that will deliver optimum hydraulic behavior and increased dynamic operating range, increased power output, increased efficiency, and optimum residual life. So in 2014, we went out to tender. We appointed an engineering professional services provider. They then went through a process of looking at a risk-based process of looking at the current condition of the plant. They did a review of the plant and system status, then identified all the risks, and then looked at the risks and tried to quantify them in terms of if something were to fail catastrophically, what would the impact be on capital expenditure, capex or opex? And then based on this, they started to develop a plan for us. And then on the right-hand side is what came out of the risk analysis. So it just listed the items which were most at risk based on the work that was done at the plant. And then 3 options were given to us, and the city decided on the 3rd option. So option 1 aimed to address the most significant risks and ensure that the plant could operate another 20 years. Option 2 was over and above option 1, which aimed to address all remaining high impact risks. And then option 3, which is the one that the city ultimately decided upon, was, as it says here, similar to option 2, but includes the possibility of increasing the capacity of the turbines and hence also the output or kilowatt and megawatt output of the machines that we have here. Okay, so just sort of coming to a conclusion and closing out. So in 2016, 2017, we started formulating a tender with the engineering company. In 2018, we went out to the market, we advertised. We had 2 interested bidders that tendered, but we were unfortunately not able to get the tender across the line for a variety of reasons. Mainly on the technical side, it looked like both companies probably were able to do it, but just in terms of management of risk, upfront payments, legal reasons, supply chain reasons, and more related to the management of the contract that we were not able to award in 2018, in 2020, 2021. We then canceled the PSP contract, and then so we started that process again. We are just about to, in fact, I think they've signed recently, and so we're going to start that process again in 2024, in early 2024. And then hopefully, if all goes well and we're able to get out to tender this time, that we are able to fully refurbish the power station. So post 2018, one of the things that popped up is that we discovered that we were running into some issues with our civil structures, referred to as ASR, and ASR, I just wrote it down here, stands for alkali silica reaction. So that's the aggregate that was mixed into the process when the power station was built, but it's almost like a cancer for concrete. So we picked up some deterioration in the structures due to ASR. And then we also had to put in remedial actions to be able to deal with this. So we are dealing with that as well. So this was not initially part of the original tender, but it will form part of the tender going forward. So it looks like the next tender that will go out, it will be divided a bit differently in terms of there'll be a civil portion, mechanical portion, and an E&I portion instead of one big tender. So. Okay, in summary, so electricity for the city is bought from Eskom at the time of use tariff. Steenbras pump storage is able to shift the load from peak time to off-peak with daily and weekly cycles. Our plant is reserved for load shedding mitigation. As mentioned, from early next year to 2031, we are hoping to complete full refurbishment of the power station. And then just to close out the major operational benefits of the power station, I think I've covered quite a bit of it. But as stated earlier, we have an efficiency of around 70 to 80%. We can generate up to full load each unit fairly quickly. It takes about 3 to 5 minutes to get to full load from standstill. And then also we are able to get from full load 600 RPM back down to standstill quite quickly. We have minimal pollution or waste. And I think the big thing that is out in the public that as a result of Steenbras power station, we are able to mitigate for 1 to 2 stages under the national level of load shedding. And then in terms of what I've mentioned earlier, we pump off peak, and so obviously the costs are a lot lower, and we generate during peak, so we have increased income. And as they say, I think flight, that's my story. Thank you so much.
Thank you so much, Dion. I know at one point you were worried whether we are still with you. I do believe that the audience has been with you, and we actually did receive some questions. So thank you so much for your passion. I think it's showing the number of years that you have been hosting this technology, as well as, I guess, the benefits that you've shared with us, what the city has been doing in attaining with the pump storage. It has been an interesting cross-cut of electrical engineering, or rather of engineering disciplines, with the mechanical side of, your rotors and the status, and some of the monitoring that you guys are doing, from the telecontrol with the SCADAs and stuff, as well as from the chemical side of things in terms of the flows that you need to monitor and maintain on the station. So it's been fascinating, and I trust that the audience has also gained something new this evening. I will take you through the questions. I think I'll just go through them as they've popped on, in terms of from the first one that has been asked. The first question was asked from Hagai, and his question is whether there is scope for enlarging the lower dam in order to increase output to mitigate against load shedding.
Yes, so a large portion of the land, can you still hear me now, Nikki? The
That's
audio
right.
still fine. So in terms of the profile that exists here, the initial exit from the power station is quite low, but then it comes a bit higher. So I think the study is going to look at making the rest of the dam floor lower, and then there's also a sizable portion of land that is part of the power station that can also be removed and make quite a bit more space. So there is a bit of scope there. We are engaging with via professional services contractor to look at that specifically, and obviously do the detailed study there. So yeah, but in terms of the size of what we are able to do there, I cannot say at this stage, but there is definitely a plan to possibly do that. What would be ideal is if we could run off the water a bit more quickly in terms of sending it to waterworks or to some other facility or function. We obviously cannot run it off into the sea, or we will get ourselves killed very quickly. So yeah, that's the big thing, that we don't know where to send the water quickly. But in summary, we are looking at extending the footprint of the lower dam so that we have more than 2,200 megawatt hours capacity on the bottom there.
Thanks for that, Dion. And I guess that will also have to take into consideration the rest of the components, including the age, as you were pointing out, some of the issues that you guys have been experiencing with the switchgear and the like.
So one thing I forgot to mention, Nikki, is that inside we did raise the portion of the dam a couple of years ago, I think 15 or 20 years ago. So obviously we've got some monitoring equipment, piezometer monitoring equipment within the dam there, so that will all form a part of the study to see that should we do X, Y, Z, ABC to the footprint, do we need to do anything to the dam wall and the spillway and the actual physical structures, and yeah. Also coming back to what you were saying, that it has to be a holistic approach, because there are some other issues that we are dealing with, and at the exit there's quite a bit of concrete as well, so we've got to bear that in mind. And especially at the lower end where the water comes out of the power station, which is quite a distance below the surface of the water, there's quite a bit of leaking in the basement on the bottom there. So extending the footprint of the dam may also have an impact on that. So it's not just a straightforward thing of starting to dig and making it bigger. It's quite complex.
Thanks for that elaborate response. I think I'm just noting we we have about 15 minutes left to wrap up. In case we don't go through all the questions, I think we will just note all of these and hopefully send the response back to the participants. The second question that was asked by Hagai was the nature of challenges faced when synchronizing these units to the Eskom grid. I think you did touch on some of the challenges that you do experience when you're synchronizing the units. Do you want to?
Sure. Yeah, yes, I think the biggest issue, Naniki, is that our equipment is what you refer to as like the phase 1 stuff in protection. It's older, not microprocessor CPU based. So there's a lot of actual moving components within them, and they still work, they're still fine, but they're obviously a lot less sensitive than modern day equipment. So that's the major issue, that the tolerances on our synchronizing equipment are not as good as what they are today. So yeah, it takes a bit of, there is obviously an operator that, not everything is automated. There's an operator that also has to read dials, actual analog dials, and then make a decision in terms of when he switches certain things on. And also the bigger issue is that there's a lot of instability in terms of the actual network. So obviously it's looking at what the power station is wanting to output and comparing it to what's coming in from the grid. And because the grid is hopping around all the time due to various factors, so we do struggle quite a bit in terms of getting that done. And sometimes that's the reason that it's not 3 or 4 minutes, that it can take 5 or 6 minutes, and sometimes we are not able to sync, and then we've got to start certain processes all over again.
Appreciated. And I think what comes to my mind is as well how CT utilizes the pump storage in the event of having to black start the power system. I understand from Eskom's perspective, we do have Pumped, which is right next door to Steenbras. That's also in the philosophy of how the grid is starting. So this aspect of how quick you can synchronize is critical. The other question that is being asked is, what is the control system brand that is used at Steenbras Power Station?
Okay, so the majority of the equipment was installed by Siemens. So a lot of the excitation system is Siemens. A lot of the old PLC stuff is Siemens. So if it hasn't been upgraded in the last 15, so on the protection side, it's been upgraded. So we have some newer ABB stuff. And on the SF6, we have some controllers. They are also ABB bay controllers, but the older vintage stuff would then all be Siemens equipment, and that's proving to be challenging for many reasons, because number one, you definitely cannot find any spare parts and components, and then secondly, if we don't have somebody at the power station or within the group that knows how to work on this equipment, it's difficult. So if you don't have a manual, it's not, sometimes you have equipment there, you cannot just go into the internet and search for the manual, because it's not going to be there. This power station was obviously built 50 years ago, so at the time people were not scanning in manuals. So we're actually sitting with thousands and thousands of pages of paper manuals that we need to obviously familiarize ourselves with. So that's the biggest challenge in terms of the service provider, i.e. Siemens, not having any technical support. So when we engage with them, they're wanting you to replace a whole system or replace a whole board, so which we obviously would like to do, but it has to be a measured and phased approach in terms of that. So, and then the bigger thing is that I think with people getting older, Naniki, or getting closer to retirement, and some people going off, that the old heads are now going off, and we're struggling when we lose 1 or 2 people. So specifically within our group in E&I, we've got 2 gentlemen who are 59 and 60 respectively, and they are experts in their area. So yeah, my biggest asset within electrical and instrumentation maintenance is my 2 staff members that I need to keep happy at all costs, because if they're not happy, then it literally means load shedding for the city of Cape Town. So
it's not just the control systems, it's also the human element of
yes, no.
how you keep this running. All right, there's a question from Graham, and I think there's a few questions. I might not pose all of them that he has posted. He's asking, what other energy mix is City of Cape Town looking at? Does the city only have the 1 pump storage and the 2 gas turbine systems?
So currently, the city's got small generation capacity at certain plants. I'm not very familiar with it. We have another directorate within energy called Sustainable Energy, and they came about in the last 5 to 7 years, or if not a bit more, so maybe 10 years. And so that leg of the city is looking at newer technologies and renewable technologies. So at certain plants, we do have, for instance, within waste, we would have capacity to do certain things. Then small little generation, maybe 1 or 2 megawatts there. But coming back to the question, Aniki, we only have one hydro power station at the moment, and then we have the 2 gas turbines that I'm aware of. Then the city is rolling out quite a bit of PV and photovoltaic and battery systems. I think they're starting internally. I attended a presentation recently where they've done some of the bigger depots in water and in facilities management. I think the Gurud Traffic Control Center had quite a big installation happening there. So that's a big drive of our sister directorate within energy. And then going forward, the city is also then looking at other options in terms of the energy mix. One of them being looking at gas turbines. So are we going to continue to operate the gas turbines at Athlone and at Rochabai? Because obviously being also older vintage machines and equipment, they are in need of some TLC and maintenance. So do we refurbish them, or do we run them to end of life and then buy new gas turbines? So the city is looking at the gas turbine option, but then the challenge becomes what kind of gas turbine are you going to run, and then what fuel source are you going to use? And the big thing becomes is how do you get the fuel in and out in terms of gas turbines. And then I know that, yeah, the city obviously looks at what Eskom is doing, looks at what the CSIR has recommended and all sorts of things, and looks at the energy mix going forward. They're busy with a 7 megawatt, I think it's been awarded, a 7 megawatt PV installation out in Atlantis, sort of an industrial sized scale PV installation that's been awarded out there. So that should be happening in the next 2 to 3 to 4 years. And then I know the city's got a big drive towards the solar and the PV side of things at this moment in time. And then obviously, as we're all aware, that we've tried to open up the market to IPPs to procure some power there. So.
Thanks for that, Dion. So it's interesting that Graham has phrased his question with the energy mix part, because I know, I mean, we as a energy entity, we've been waiting in anticipation for a revamped IRP, right? And I noted from the last 2019 IRP that hydro has been allocated about 2,500 megawatts. Whether that has a portion of it, including pump storage, who knows? But I guess we will all still keep our eyes peeled on when that update of the IRP comes out. The next question that Graham has asked is, are these units able to operate in synchronous condenser mode to assist with grid stability?
So the answer is yes, they are able to provide megavar compensation. I think it's in one of the slides there. We can do about 30 megavars. I think if we are running the units in certain modes, where we run them in certain modes, we are able to do that. But we don't do it anymore, Naniki, because preserving the machines for Gen Pump is too vital and critical. So in the 10 years that I've been here, I've never seen or heard of it being done. But it does have the capacity. I've got it somewhere here. I can certainly send it through to Graham in terms of, there's a technical sheet that I'll maybe just share with you, Naniki, that you can send out. But the answer is yes, we can do synchronizing condensation mode.
Also a critical one in the space that we're operating in, as we've seen, obviously the levels of load shedding, stages of load shedding increasing, and some of the public conversations around system stability, around risk of a grid collapse, and that. So that part of grid stability and what megavar support you can get from the units, definitely an important factor. There's a question from...
Just to add on to that, Naniki, I know that in my time in Eskom that we had a very rugged program of rolling out in terms of grid security. We had a very rugged program of running out the under frequency load shedding panels. And I know that Eskom had a big program that they ran in conjunction with the city. So I know that those things are all over in our substations. And I'm fairly confident that we will have darkness before we will have a grid collapse. That in terms of our systems that are in place, our actual automated systems, and then also the operating protocols that are in place, that we will sit in darkness, but not because of a grid collapse. It will be an intentional load shedding exercise.
That's right. System operator would be happy to hear you say that.
Yeah. Good off, yeah.
Tony has asked a question as to, would it not be better to install battery energy storage system to work in conjunction with the pumped storage? Has there been any studies along battery energy storage? I guess he's asking specifically for the city of Cape Town.
So one of the exercises that our sister department, Sustainable Energy, looked at was they ran an exercise in terms of looking at 2,200 megawatt hours, which I was speaking about. And they looked at what are the battery energy storage systems available commercially, the big systems on the market. And I think so to rebuild this power station as is would cost about 4 to 6 billion rand. That's what I've been told. But to have an equivalent of 2,200 megawatt hours battery storage capacity, we ran the exercise and they did some maths on it on that side. I think the figure that I heard, Naniki, you were looking at 13, 14 billion rand just for the battery storage. So from a financial and economical standpoint, it doesn't make sense to go that route. So the technology for large scale storage is not there. I know the city is looking at a lot of things like bring it down to distribution level. I've sat in 1 or 2 meetings where they're looking at substation level to have 1 or 2 feeders there within substations that when there's power, you'll charge up and then you'll charge your battery systems there. But we still are far away from practically implementing that.
Yeah, I think the one article that I came across that talks towards this was where they're talking about the disadvantages, at least from a pump storage perspective, in terms of the environmental aspect. And I recall when I did a visit in Palmit that this was attended to quite extensively. But then the other issue, I guess that's more of a concern, is the turnaround times, the length at which you're from a project development to commissioning a pump storage versus putting down a battery energy storage. Perhaps maybe that might be one of the biggest differences between the two.
Yeah, fair point, Anik. And I think the other big thing which I forgot to mention is that also in terms of the size of that kind of storage capacity, the footprint that it leaves is massive. I think we were talking about a good couple of 100 football fields. It was done a couple of years ago, but it is massive, massive, massive if you were to replace the dam with energy storage. And then also along with that, as you are alluding to, the project management side of it, and also the environmental impact assessment side of it, that you're going to run into a lot of challenges there in terms of doing those kinds of things. So yeah, it's an interesting concept, but yeah.
To honor our time contract, maybe I'll just ask 2 more questions and then we will bring it to a close. Andile has asked a question. If I heard correctly, you said there's unlimited supply of water at the top. Why do you then have to pump up all the water instead of supplementing from the water source to save costs? Is that possible?
Yeah, so I think the major constraint is the size of the lower dam and the bottom here. So we can only run to a certain amount of megaliters down here, and then we cannot generate any more. So, and then also in terms of if the dam and the bottom becomes too full, then it also affects the net operating head, and then you have some issues with the vibrations on your machines. So yeah, our limit is the size of the bottom dam at the bottom. So we have to send the water back up again. And maybe I didn't use the correct term to say unlimited, but there's a lot of water coming from Palmit side and further up here.
When we mentioned Palmit, Graham has also asked a question here. Is the operation of the Steenbras station coordinated with Eskom's Palmit station? And maybe the last question also, what is the cost difference between generating and pumping operations that came through from Craig?
Okay, so in terms of the first part of the question, we don't coordinate with Palmit in terms of how we operate and run the site. What I can say is that just as an aside, in 2018 with the local droughts here in Cape Town, that there were discussions that had to take place with people further upstream and with us down here, Palmit and bulk water, because at one stage it was getting to a point where we were probably a month or two, maybe 3 months away from having to make a decision in terms of, are we going to generate and use water so that we can have electricity, or are we going to use the water for water in terms of sewage and consumption? So no, we don't coordinate in terms of our operation here. The second part of the question, Aniki, the difference. Yeah, I think I did cover it in one of the slides in terms of the tariff, but to get specifics, I can get that detail to you. I'll just make a note, and then I can rather just chat to the guys on the tariff side and network control and get the specific amounts. What are we paying to take off the grid? What are we getting to put onto the grid? And then I'll send that through to you. But as I said, yeah, it's at least double, if not 3 times the ratio in terms of spend versus income. But
appreciate it. Maybe to squeeze one last question. Thank you very much for such an informative presentation. That's from Andries. Are there any useful lessons during drought close to day 0? So what we experienced.
Yeah, I think just from a human perspective, Naniki, is that within the city we on a database where we get the weekly updates in terms of what's happening with the water. So and working at a hydropower station, maybe I didn't always appreciate how important the resource was. It was, you know, just something you open up the valves and the system runs. So it's certainly when we got to a point of having serious discussions about not being able to generate anymore, and it was very early discussions, but it was brought to our head of generation to start looking at what are we going to do, because at some point the water at the top was starting to lower, and then you wouldn't have enough water or net head to be able to operate. So it just made, from a personal, not even a professional perspective, just appreciate the resource of water a lot more. And yeah, I suppose we must just always remember the bad times from a couple of years ago. We've become a bit slack, and we've been blessed with a lot of rain, especially in the Western Cape in the last couple of months. So we still need to be vigilant and still keep conserving, I think, is the lesson that I've learned there.
Truly appreciated. Thank you so much, Dion. I think your passion in terms of the subject matter has been proven, and we appreciate your time that you've spent with us this evening, opening the turbine rooms and showing us the status as well as the road tours. Appreciate that. And I think as we been moving into the space of the advancement of technology, we're talking about battery energy storage that is coming online. We do appreciate that these are the technologies that have brought us to where we are now. And there's obviously benefits, as we've had, that has assisted, at least within the city of Cape Town, to alleviate the higher stages of load shedding. And obviously, you may be aware as well that we have the likes of Drakensberg, as well as Ngula Pump Storage, which I think is the latest one that was installed within the South African pool. And like I indicated, that the IRP 2019 is talking about 2,500 megawatt of hydro that is allocated for more extension of our energy mix. So colleagues, I would like to take this time to thank you for your time that you have allocated to spend with us and away from your families. I know it's the end of the year and most of us are feeling fatigued, but it's also an exciting time within the energy space, particularly energy storage. As I shared in the beginning, that we had that award of the first battery energy storage IPP that was announced. And from here on, I think it can only be the best in terms of how we are putting our hands together to tackle the energy security. So thank you so much for your time. And remember to have a look at the handouts. If you can do downloads of latest issues of What Now, and also if you would like to join SAIEE for events like this, in how we ensure that we keep our continuous development points as we go on. So enjoy your evening, and thank you for joining us.
Thank you. Thanks so much, Enrique. Keep well, man. Cheers, man.